Good afternoon. Before I start talking about tritium today, I'd like to acknowledge my co-authors on this talk, Stu Hamilton from the Ontario Geological Survey, Alex Lemieux from Chalk River Nuclear Labs, and Ian Clark from the University of Ottawa. From the mid-1950s to the early 2000s, tritium was one of the most useful groundwater tracers that we had. The 1963 bomb peak was a classic time marker in most aquifer systems and was used to estimate groundwater velocity. And you can see it really clearly in the Ottawa precipitation data I'm showing here. But since then, the 1963 peak has been assimilated in most, if not all, groundwater systems by decay and dispersion. The annual average tritium concentrations in Ottawa are stable, but what about the rest of Southern Ontario? And how about the groundwater systems? Our research objectives are to interpolate shallow modern tritium concentrations across Southern Ontario and then investigate the reliability of this interpolation as an input function that could re-establish tritium as a useful groundwater tracer. So our approach was to select a subset of wells from the OGS ambient groundwater dataset that represents shallow modern groundwater conditions, use those samples and interpolate the tritium concentrations for these across Southern Ontario, assess the quality of the interpolations and make adjustments, and then repeat this until we arrive at a reliable version of the interpolation. The Ontario Geological Survey Ambient Groundwater Geochemistry Program has sampled 2,516 wells in Southern Ontario. And the first step of this project was really to decide which of these wells represent those shallow modern conditions that we're trying to capture. So to establish our subset of wells, we considered well type, well depth, and geology, and also tritium content. So we divided all the wells into type and depth groupings that are shown in the table here, keeping the board wells and sand points separate, overburden wells separate, and also bedrock wells separate. And for the bedrock wells, we considered well depth and overburden thickness in our groupings. So once the wells were divided up, we plotted the cumulative probability plots for tritium for each of the well groupings. So this figure shows the cumulative probability distribution for each well grouping as a single line on the plot. And I've put some horizontal markers on the plot just to guide your eye. So at the top is that Ottawa precipitation median at 15 tritium units, and below that, the red line below, at 8.6 tritium units is the 10-year decay concentration, assuming plug flow from the Ottawa precipitation median. And from this, we established our selection criteria to comprise well groupings that have a 50% probability of containing tritium levels equal to or greater than 15. And so the lines would have to go through there. And an 80% probability of containing tritium levels greater than or equal to 8.6 tritium units. So our distributions, again, would have to go through the second line. So the well type and depth groupings that made the cut are highlighted in this table. And here's a look at all the data together. And now we're looking just at the data from the well groupings that made the cut. So of the 2,516 wells sampled in Southern Ontario in the ambient groundwater program, only 630 wells are selected to represent the shallow modern conditions that we're trying to capture. So here's a first look at our shallow modern tritium data set with sample points color-coded to reflect tritium content. And the range of values is 0.4, which represents half of the detection limit, to 110 tritium units, so a really big range. And we can already see clusters of high and low tritium trends across Southern Ontario. And when we look at the raw data, we see the mean and median hover around the median annual Ottawa precipitation value, and our histogram shows us that the data are nearly normally distributed but skewed at the high end. So we have chosen empirical Bayesian kriging as our interpolation method because it works well for values that vary in how they change in space across the model domain, like the clusters that we're seeing here. So, and here we have the first version of our tritium interpolation for Southern Ontario. And immediately we see the high tritium areas in red and orange that are influenced by nuclear plants at Pickering and Darlington on Lake Ontario and the Bruce plants on Lake Huron. We also see an area of high tritium in Windsor, which may be influenced by the Fermi plant in the US, which is labeled. We can see some variability in Ottawa. Is that really real? I'm not sure. And an area of low tritium on the Niagara Peninsula. So the overall statistics for the model are pretty good. The mean error is close to 0, which means the model isn't trending to either over or under predict tritium values. And the RMS standardized is close to 1, which means that the model is estimating the variability in predictions pretty well. So when we plot measured versus predicted tritium, we get an R² of 0.4, and we see that the biggest differences occur in areas where our measured value is near 0 or very low, and the model has predicted a much higher value. And you can see that those samples are circled in red. So to improve the interpolation, we removed samples that don't represent shallow modern conditions. So remember, our method for selecting these wells wasn't quite perfect, but we needed to remove these samples in a defendable way. So as a start, we calculated the relative difference between predicted and measured tritium for every sample. And in the plot of residuals on the bottom left, the largest relative difference, greater than 2.5 times, those samples are highlighted in yellow, and they comprise samples where the model has over-predicted the value. So wells with a relative difference greater than 2.5 are also plotted in yellow on the map and are generally clustered in 3 areas. And we investigated each of these samples individually and found that they actually don't reflect shallow modern conditions at all. Instead, in Ottawa, samples from these wells are influenced by Champlain Sea chemistry. We have high TDS and methane. In the Laurentian Valley area, these samples occur in lowland areas at the end of longer flow paths and tend to contain high methane. And on the Niagara Peninsula, these samples are impacted by brines with high TDS and hydrogen sulfide, as well as chloride-bromide ratios that are common to local brines. So with those 24 wells removed, here is version 2 of our tritium interpolation on the bottom right. So although the major trends remain, there are some key differences between the 2 versions. In version 2, we see that on the Niagara Peninsula, the areas of higher tritium in yellow are expanded. And near the Pickering and Darlington nuclear plants, we see the very high tritium area in red has also expanded. And near Ottawa, the higher tritium zone has also expanded. We see less green and more yellow. And the statistics for the model also improved for version 2, with the R² between measured and predicted went from 0.4 for version 1 to 0.6. To further investigate the trends near the Bruce and Pickering and Darlington nuclear plants, we took a look at wind direction. These wind rose diagrams are developed from wind monitoring at 10 meters above ground, with data averaged over the past 30 years. So near the Bruce plant, the wind direction is predominantly west to east, moving tritium emissions from the plant onto land. And wind data from Toronto shows a southeastern to eastern wind direction trend, really moving tritium emissions and precipitation from the plant onto Lake Ontario. So these wind trends are reflected in the size and shape of the tritium areas that we see in groundwater near the plants. The Pickering and Darlington plant impact is really smaller and hugs the shore as wind moves emissions to Lake Ontario, whereas the influence of the Bruce plant is larger as wind pushes precipitations and emissions onto the land surface. So for our tritium interpolation to provide an accurate recharge end member for shallow groundwater at any location in Ontario, the tritium in groundwater has to be pretty stable over time. And we've seen stability in annually averaged tritium data for Ottawa precipitation. I showed this on my first slide, but what's happening near the nuclear plants in precipitation in groundwater? We plotted long-term monitoring data from the Bruce nuclear site and the Pickering and Darlington sites. The nuclear plants monitor nearby shallow domestic wells for tritium concentration annually and the locations of these monitoring wells are shown in blue. And what we see for both monitoring areas are big fluctuations in tritium in precipitation, and despite this, relatively stable concentrations in groundwater. The standard deviation of tritium in groundwater for both areas is about 25 tritium units, which is roughly the detection limit of the non-enriched analyses method that was used. So consistent tritium concentrations in groundwater near nuclear plants, where we know tritium in precipitation varies the most, supports the use of RMAP as a reliable local modern tritium estimate. So as far as next steps go, version 2 is not the final version. We are still working to improve the quality and reliability of the interpolation. We plan to publish the map and accompanying data sometime in 2021. This publication will also include the error assessments and the reasoning behind the selection of empirical Bayesian kriging as our interpolation method, aspects that I didn't have time to discuss today. And I'll end with some final thoughts. So tritium was a very useful tracer prior to that assimilation of the 1963 bomb peak, but since then it's become difficult to make groundwater age estimates without also collecting helium data as well. What that 1963 peak provided us was a really useful time marker, and what our interpolation offers is an alternative marker, a location-specific recharge end-member tritium that can provide context for interpreting groundwater tritium values in systems anywhere in Southern Ontario. So we look forward to sharing our final version with you, and we want to thank you for your time and interest today.